In this video, I'm going to talk about the classification of lipids. Lipids are typically put in the same categories as that of proteins, carbohydrates, and nucleic acids. However, the difference really is lipids are not really considered polymers, but the rest of the guys like carbohydrates, you got proteins, you got nucleic acids. Nucleic acids are like DNAs and RNAs. They are all considered polymers, but lipids are not really polymers, so they're not really going to be as big as something like proteins or carbs and the DNA and the RNA. So let's go ahead and classify the lipids. So when we look at the lipid, we can go ahead and put those into two categories, where one of the categories is going to be the fatty acids and the other category is going to be the steroids. So let's come down to the fatty acids for a minute. So in a typical fatty acid, you would have a carboxylic acid functional groups like you got on the right side here, and you're going to have a long tail here, which is going to be made of just carbon and hydrogen. So this long tail of carbon hydrogens could be made of 16 carbons, could be 18 carbons, could be 20 carbons, and so on. So based on that analogy, I can say that this end right there is going to be relatively polar because you got the carbonyl and the OH there, and the other end is going to be nonpolar. However, if there is no charge on there, so I can say this is going to be relatively polar, and this one is going to be relatively nonpolar. But if there is no charge on this fatty acids, or another way of saying if it's not deprotonated, the fatty acids usually do not dissolve in water. That's because the big long tail of this hydrophobic nature kind of dominates over this small polar group. So as a result, you're not going to be able to dissolve that in water. However, if you could somehow get this guy, like for example, if I just go ahead and copy this here. Hold on a second. This one is better. So if I go ahead and put this and remove actually the H from there and rather creates a negative charge on this one. So as soon as you create a negative charge, it becomes like an ionic. And in that case, you would be able to dissolve it. So remember, a polar group can only handle up to 5, 6 carbons in the chain. And as soon as it goes over 5, 6 carbons in the chain, then it relatively becomes insoluble in water. But if you have a negative charge or a positive charge, like you got a negative charge on this oxygen here after removing that hydrogen, a negative charge and even a positive charge can handle up to 20 to 25 carbons and it will still be able to dissolve in water. So that's how great the power is as soon as you get a negative or positive charge on the molecule in terms of the solubility in the water. Now, I can go ahead and classify the fatty acids into four different groups in there, and they're gonna have some other subgroups in there, but these are like the big categories in there. So you got these waxes that you got, and a wax typically going to have a long chain of an alcohol and a fatty acid. So again, the fatty acid is just going to be this guy right there, and you're going to have a long chain of the alcohol. So what that technically means is I can have, let's say, a really long chain of the alcohol. So that's going to be the alcohol, and it's going to be hooked up with the fatty acid. So I can probably draw the fatty acid with a different color here. So this is going to be the fatty acid. And fatty acid itself is going to have a really long chain in there as well. So at the end of the day, you do have an ester functional group in there, but we categorize those in the VAX here. That's because even though you have a very small polar group in there or the presence of these oxygens, but those are kind of shadowed by these non-polar groups on both sides. So as a result, that does not really dissolve in water. As you can see, none of the vaccines that you got out there, they're not going to be soluble in water at all. So that's how these vaccines going to look like. So make sure you know the functional group in there, you know what's on the one side and what's on the other side, basically. Now, in addition to that, you also have these triglycerides or triglycerols, you can say. And the triglycerols, you would have a glycerol functional group. So glycerol functional groups would look something like this. I would have a CH2, CH, and another CH2. and obviously these going to have the OHs, but when it has an OHs, you call it glycerol, but these are going to be hooked up with the fatty acid. So I'm going to have, let's say, a fatty acid here, and then you're going to have a really long chain here. And I can say the same story on the second one. And these fatty acids may be the same and may be different, so that doesn't really matter whether you have the same number of carbons on each of those individual fatty acids. But at the end of the day, you're going to have these long chains. They could be 14 carbons, 16 carbons, 18 carbons, stuff like those, and they could very well be different from one another. So that's what the triglycerides are. Now, these are also called fats if they actually gonna be the solid. So if you have a triglyceride that's actually in a solid, we typically call that in a fat. And if it's and you can also have the fatty acids as oils. So oils are going to be in the same category if they are liquid, obviously. Um, in addition to that, you also can have this glycerophospholipids. So the difference really going to be in there is you still got this glycerol here, and you got this. Two of the groups are going to be the fatty acids, and one of them is going to contain the phosphate, and it's probably going to have an amino alcohol in there. So if I want to kind of give you an example on that, so I'll probably just copy this down here. And so one of the groups that's really going to be different is this really last one here. So instead of that, I'm going to have a phosphate group in there. So that's going to be P double bond O, oxygen there. And then I'm going to have an alcohol. So typically it's two carbon, like an ethanol. And then this is going to be hooked up with an amine group. And a lot of time that amine group is usually protonated. So you have a positive charge on this. So now you may wonder, like, what's really the significance of that is this glycerophospholipids or phospholipids itself, they are actually the part of cell membrane. So you know how cell membrane is an bilipid layer? That's because this part right there is a hydrophobic part, so that's going to be embedded in the cell membrane, and this part right there that's going to be relatively hydrophilic because it's got a positive charge. And even if you don't have this guy right there, the phosphate group itself is going to have a negative charge on there as well. So this itself is going to be exposed outside the cell membrane, and that's going to be water loving, you can say. So typical cell membrane looks like this, where you have this, and then you also going to have the same thing coming from inside. So those two lines that we've been drawing on every single dots there, they represent these hydrophobic tails of these fatty acids here. And then the circles they got on there, they eventually are going to be hydrophilic because they're going to be containing this phosphate and ethanolamine group. And if you don't have an ethanolamine, you can just literally still have the phosphate group, which is still going to be polar. So that's what we're really looking at in there. In addition to that, you can also have these sphingomyelins. What those sphingomyelins really are is you're going to have this carbon chain here, and on the top, this is also going to be containing just the carbon. So it's going to be a very hydrophobic chain. It does not have any ester function groups in there, but just carbons. It could have possibly in a carbon-carbon double bonds up there, but it's just going to be in a simple carbon chain. And then you're going to have this, the middle one is going to be hooked up with some sort of fatty acid in there, and then um, they will have a nitrogen embedded in there, so that's going to have like an amide function groups. But on the bottom, what's more important that you're going to have this phosphate and an amino alcohol in there, which is going to be very similar to the phospholipids here. But the really difference between the phospholipids and sphingomyelins in there is how the top part is really going to look like. So you have two fatty acids in case of phospholipids, but in sphingomyelins you only have one fatty acids, and the top part is just a continuation of this carbon chain, which is only going to be containing carbon-carbon bonds, and possibly sometimes you may have a carbon-carbon double bonds in there, but that's pretty much it. Now, along with this category of lipids, which is the fatty acids, you can also have steroids. So now where the steroids really come from, and what's really the functionality of those. So one of the things, the common things you would possibly see in steroids is you actually going to have four rings rather fused in there. So three of them are six-member rings, and then one of them is like a five-membered ring. And these makes up a lot of hormones in there. Like you can talk about cholesterol, you can talk about um, like testosterone, you can talk about bile salt. You can talk about a lot of those things. They all kind of fall in this particular category. So if you see something that is containing four rings, and the three of them are six-member rings, and then one of them is a three-member ring, a five-member ring, that will put them in a category of steroids. So like I said, they do include a lot of these hormones that includes testosterone, cholesterol. You can talk about estrogen and estradiol, progesterone. All these things, they all fall in the categories of the steroids. So this is what really the classification of lipids.